Welcome to the 29th lecture of combinatorics. In the last class we were looking at the how to use generating function to solve certain counting problems, right. So, the last question we looked was, finally the issue is to extract the coefficient of say x to the power n from a generating function, right. So, when you expand that generating function, what would be the coefficient of x to the power n? This is what our that will give you the final answer. So, the way we modeled certain problems as for certain part of the solution was getting as for instance in the question as we considered up to now, we were counting the number of solutions for an equation like this, E1 plus E2 plus Ek is equal to n with various conditions on E1 equal. The basic condition is that E1, E2, Ek etc. are non-negative integers, right. But we may have extra conditions like E1 has to be an odd number or E2 has to be an even number, and such conditions are possible, and also we can restrict the values that say an EI can take, we can several such conditions are possible, right. And now corresponding to each E1 we will have one term like this, say 1 plus say here x cube plus x raised to 5 plus, like that we can put when for instance. So, okay, x plus x cube plus this will say, this will kind of impose the condition that E1 is always odd, because what corresponds to E1 is the power of x which will come from this first part, right, and E2 will be coming from something like this, and we can cook up this stuff, construct this sum in such a way that the conditions on E2 are satisfied. Like that we can form, and finally we will get an expression for this product, and the coefficient of x raised to n in that is what we are interested in. Yesterday we came to some form like say x to the power 7 minus say 1 minus x square to the power, so 1 minus x whole square. So, what is the coefficient of x to the power n in it, such question. We first noted that to find the coefficient of x raised to power n in this, we only have to look for the coefficient of x to the power n minus 7 in say 1 by 1 minus x square to the power 2 into 1 minus x whole square, right. We can drop this x raised to power 7 because that is already accounted here, because every term is multiplied by x raised to 7. So, x raised to n will come from x raised to n minus 1 7 of the expansion of this thing, right. So, now we only have to concentrate on this thing. We identified that this is of the form f hx equal to fx into gx, where fx can be written as 1 by 1 minus x square whole square, and gx can be written as 1 minus x whole square. You know, for both of this thing we know how to get the expansion, because here we know this is 1 plus x raised to alpha form, where alpha is equal to minus 2, and so here instead of x we may have to use, so for instance we can substitute y, yeah, so instead of x we have to use minus x square, that is all, right. Then we substitute or say some use some substitution like y is equal to x square in it, use y here, and then wherever y raised to I appears you substitute minus x square for y, right. That will give you the expansion of this thing, right. And similarly g minus x, the expansion of this thing will be yeah, g minus x expansion of this thing will be, you put alpha equal to minus 2 and y equal to minus x you can take, and then you substitute using the formula for this, right, expand using the formula for this thing. Now for instance, if you know the sequence corresponding to say suppose A0, A1, A2 etc. correspond to g fx, right. That means fx equal to A0 plus A1 x plus A2 x square plus and so on, right, and gx equal to B0 plus a B1 x plus B3 x, sorry, B2 x square plus and so on, right. Then let us say hx equal to fx into gx, say let us write this as C0 plus C1 x plus C2 x square and so on, right. Then we say that Cn, then x, the coefficient of x raised to n will be given by A0 into Bn plus A1 into Bn minus 1 plus A2 into Bn minus 2 and so on all the way to An into B0. Why is it so? Because A0 into Bn, where is it coming from? Because this A0 will multiply this, sorry, this is B2 x square. So, say Bn x raised to n, this A0 into Bn x raised to n, right. So, that is why that way we can form an x raised to n with coefficient B0 into A0 into Bn in fx into gx. Similarly, A1x into say Bn minus 1 x raised to n minus 1 here, that x and x raised to n minus 1 will form an x raised to n, and A1 into Bn minus 1. So, similarly A2 into Bn minus 2, these are all will form coefficient of x raised to n in the product, and we have to sum up all those things, right. That is how we will get Cn, that correspond to Cn, right. We can once we create once we get the sequence for fx and gx by using this formula here. So, we can, after that we can yeah, we can use this technique to get the formula for content. Of course, so we are not explicitly evaluating it, we are only giving it as a sum. I just wanted to introduce this concept of how to find the coefficient of hx, where hx is equal to g of x, f of x into g of x, where the sequence corresponding to f of x is known to us, and the sequence corresponding to g of x is also known to us. Then we can, how to cook up, how can we find out the coefficient of x raised to n in the expansion of h of x. That is what we discussed here. Of course, okay, this kind of like complicated formula, how it will be useful is not very clear, but at least we can compute it, right. Now, we look at a example where things cancel out, and finally we will get a nice form for h of x. So, just for like making you aware that such a possibility is there in some cases at least. Determine the generating function for the number hn of solutions of the equation. Sorry, before that here, find the number hn of bags of fruit that can be made out of apples, bananas, oranges and pears, where in each bag the number of apples is even, apples have to be even. The number of bananas is a multiple of 5, the number of oranges is at most 4, and the number of pears is 0 or 1, right. These are the conditions. As usual, what we are looking for is the number of non-negative integer solutions for this equation, 3 plus E4 is equal to n, with some extra conditions on E1, namely E1 has to be even number, and then E2 has to be multiple of 5, see, recall this E1 corresponds to the number of apples, right, and E2 corresponds to number of bananas, right. I thought it's bananas, and the oranges, namely E3, oranges, it is in between 0 and 4, right. That means E3 has to be in between 0 and 4, and E5 can take only 0 and 1, E4 can take only 0 and 1. Only two possible values are there for E4, right. So therefore we can cook up the corresponding terms for this. How do we do? Even terms. So this is 1 plus x square plus x raised to 4 plus, this is the sequence, some infinite sum we will make for this thing, because E1 has to get only an even value. So the power of x's here has to be even number, right, and E2 is a multiple of 5, that is 1 plus x. See, this 1 corresponds to x raised to 0, that means it's as good as saying that x raised to 0 here, right. So now this is x raised to 5, because multiples of 5 only are allowed here, x raised to 10 and so on, right. This is easy, this is between 0 and 4, that is x plus x raised to 4, and this is even easier, this is this, because 0 correspond to this one and 1 correspond to x. Now we multiply this out, right. So the point here is that the coefficient of x raised to n in the product of all these 4 terms will correspond to the number of solutions for this equation where each EI satisfy the respective conditions given here, right. Why? That is clear, because even so if you get such a solution, definitely one term will come corresponding to that from this thing, because so there is an E1 is an even number, I can take x raised to E1 from this thing, and E2 is a multiple of 5, I can take x raised to E2 from this thing, and then E3 is in between 0 and 4, then I can take from this thing x raised to that E3, and E4 is 0 or 1, therefore I can take from here either 1 or x corresponding to x raised to E4. That because they add up to n, I will get x raised to n when I multiply x raised to E1 into x raised to E2 into x raised to E3 into x raised to 4. On the other hand, any consider any way you can make an x raised to n in this product, that will indeed corresponds to some E1, E2, E3, E4, where the power of x which came from here correspond to E1, power of x which came from the second term correspond to E2, power of x which correspond came from here correspond to E3, and power of x which came from here correspond to E4, and we know that these things satisfy the conditions we want for E1, E2, E3, E4. That is why it is the correct solution, right. Now how will you find the answer? Because the first term, as we have seen in the last class, is 1 minus 1 by 1 minus x square. The second term, as we have seen in the last class, no, we haven't seen it, but we know that it is 1 minus x raised to 5, because if you have any doubt on this one, you put y equal to x raised to 5 and consider 1 minus 1 y. This is 1 plus y square plus and so on, and this when you substitute x raised to 5 in that, you will get 1 plus x raised to 5 plus x raised to 10 plus x raised to 15 plus this is what, right. Therefore this should make it clear that this 1 by 1 minus x raised to 5 correspond to this sequence, right. And this third term is easy to find, because we already know that it is 1 minus x raised to 5 by 1 minus x, and this fourth term is just 1 plus x, there is nothing there is no need to simplify it, right. So, now we can cancel this and this, and here we have 1 minus x square, which, so of case now what will happen to this 1 minus x square is 1 plus x into 1 minus x into, here we have a 1 by 1 minus x left, right, and upstairs we have 1 plus x. So, in the numerator we have 1 plus x, that we cancel with this thing. The final answer is 1 by 1 minus x square, right. Now, you know that what we are interested in is the nth term, right. So, sorry, the coefficient of what we are interested in is the coefficient of x raised to n. What is the coefficient of x raised to n in this thing? So, that is because this is of the form 1 plus x raised to alpha, where alpha equal to minus 2, and we have a substitution y equal to minus x, sorry here, sorry, let us say 1 plus y raised to alpha and y equal to minus x here. So, nth term is going to be alpha choose n y raised to n, that is minus 2 choose n, minus 2 choose n minus x raised to n, right. This is what? This is yeah, this will be minus 2 minus 3. So, minus 3 into minus 4 into up to where we should go, we need n such sum. This is, remember what we need is minus 2 n falling factorial there divided by n factorial is what that's what this is, right. So, up to minus of n plus 1 we will get here, right, because n is starting, because we are starting by n with n, right. Below we have n factorial. So, even if we are starting with 2, so we can assume that there is a 1 here. So, actually this n factorial will cancel off with 1 to up to n here. So, only and this, what will happen to this will be minus 1 raised to n and x raised to n, and this, there are how many minus signs here, there are minus 2, minus 3, minus 4 up to minus n plus 1. That means we have this as minus 1 raised to n into 2 into 3 into up to n plus 1 into, we have a minus 1 raised to n here and then x raised to n here divided by n factorial. So, this and this together will form a minus 1 raised to 2n as usual, and 2n being an even number, that is just 1, right, that goes away. And this 2 into 3 into up to n, if you consider, that is already n factorial, that goes away, right. We just get n plus 1 into x raised to n. The coefficient of x raised to n in this thing is just n plus 1. So, the number of integer solutions for the equation we wrote, this equation, right, satisfying all these conditions, right, is indeed n plus 1. So, the interesting thing is we did not even think what we are doing, we were just manipulating equations, and we came up with this answer. It would be nice to try it out combinatorially, whether you can get the same answer using counting arguments without using these generating functions. Now, of course, this was a example to show that sometimes the terms involved may nicely cancel off, and we may get a very neat answer in the end. Next question, determine the generating function for the number hn of solutions of the equation E1 plus E2 plus Ek equal to n in non-negative odd integers E1, E2, Ek. How is that? So, we want E1 plus up to Ek to be n. So, each Ei is non negative odd integers. That means it can be 1, 3, 5, 7 and so on, right. Here I can take these values. So, for corresponding to E1 we can put one term, namely x plus x cube plus x raised to so on, x5 plus so on. Similarly, a term corresponding to E2, x plus x cube plus x raised to 5 plus so on, and like that. Ek we will get x plus x cube plus and so on. So, this is x plus x cube plus to the power k, because there are k terms like that, and this is what, x into, so x raised to k into, so I am taking x out from this thing. So, what I do is I will take x out here. So, that means x into 1 plus x square plus x fourth and so on whole power k, which is x power k into 1 by 1 minus x square whole power k. This is out. If you want the answer, you look for the coefficient of x raised to n in it, right. So, as we have discussed, the coefficient of x to the power n will correspond to the coefficient of, because every term is being multiplied by x raised to k. So, the coefficient of x raised to n will correspond to the coefficient of x raised to n minus k in the expansion of 1 by square whole power k, right. And this is familiar. What do we do? Of course, so we have this form 1 plus y to the power alpha, where alpha is equal to minus k here, and our y is equal to minus x square, right. Now, the nth term of this expansion is alpha choose n into y raised to n, right. Now, what is that? Alpha being minus k, that will be minus k choose n into, substitute for y equal to minus x square, right, minus x square whole power, but that is the nth term. So, here we are getting x raised to 2n with a minus 1 raised to n and minus k by k choose n. So, now but what we are interested in is the coefficient of x raised to n here. So, what could you do? Yeah. So, sorry, we were looking for the coefficient of x raised to n minus k, sorry, x raised to n minus k, because that is what we told, right, because in the earlier we had x raised to k into 1 minus x square whole power k, right. So, we are looking for the coefficient of x raised to n minus k. So, this is a general thing, the coefficient for x raised to 2n is going to be this. So, of course, this is always going to be an even power of x here. Now, see, we were looking for the solution of E1 plus E2 plus Ek is equal to n, right. Now, where each ei is odd. So, suppose k was an even number, this n is going to be also an even number, and n minus k is also going to be an even number, and if you are looking for n minus k here, so we can actually take, so for instance, let us put it as this as n dash is the general term here. So, n dash, right. Now we can put n dash equal to 2n dash is equal to n minus k, and then n dash equal to n minus k by 2, right. So this we can easily find out, right, put n minus k by 2, because n minus k by 2 is going to be an integer here, we can substitute here. But on the other hand, if k was an odd number, then this n is going to be odd, because the odd number of odd numbers add up to an odd number. So n minus k is going to be again even, because this is an odd number and this is an odd number. So n minus k by 2 is going to be again an integer n dash. So we can find the coefficient for that. Okay, anyway, that was just to give, like, usually yeah, we have some techniques to find the coefficients like this. To some extent we can proceed. Of course, I hope this gives some idea about how to go about doing it, right. Now the next, we look at the next question. Okay, this we have already discussed. Count the compositions of a positive integer n using the technique of generating functions. This is something which we have earlier looked at. What was the composition? For instance, 1. So 1 can be written as 1 here. It's only one composition here. We had seen this before. For instance, 2, we can write it as either just 2 or 1 plus 1. There are 2 compositions for 2, right. When I take 3, we can either write it as just 3 or 2 sum and compositions, namely 1 plus 2 or 2 plus 1. These are 2 possible ways, or you can write it as 1 plus 1 plus 1. There are 4 compositions, 4 equal to 2 raised to 2 compositions for 3, and for 4 we have, see, 4, right. So 3 is 1 plus 3, 2 plus 2, 3 plus 1, and now 3. So for instance, I can start with 1 plus 1 plus 2, 1 plus 2 plus 1, and 1 plus, that is it. So we can start with 2 here, 2 plus 1 plus 1, that is all, 4, 5, 6, 7. And we have the composition 1 plus 1 plus 1 plus 1. So this is also 4. So there are 8 compositions, that is 2 to the power 3, 4. We have seen that in general for n, 2 to the power n minus 1 compositions are there, right. So what we are doing is we are splitting it into the sum of positive integers, but we are giving importance to the order here, right, in what order we are doing, right, and how many of them are there is the question, right. So what we do now to find out this is this. So we will use generating functions to get the same answer, 2 raised to n. We already know the answer, but we want to demonstrate the use of generating functions to get this thing. So we first look for the compositions with exactly I sum n's. This is what we are going to do. So how will I do that? So for instance, if it was I equal to 1, then I can create something like this, some like this, infinite sum like this, x cure, right, and now say look for the coefficient of x raised to n in this. Definitely there is only one way to get a one sum and composition for n, that is x raised to n's coefficient is just 1 here, right. Now let us say if I am looking for the 2 sum and compositions of n, So what I can do is I create x plus x square plus, so this term, and then similarly one more term x plus x square plus x cube plus, see the not, this correspond to the first term in the sum, the sum. For instance, if I write 4 equal to 2 plus 2 or 4 equal to 3 plus 1. So I will look for the coefficient of x raised to 4. One possible way to get x raised to 4 from this to the product is to get x raised to 3 from here and x raised to 1 from here. That is why 3 plus 1 is 4. This will be found. So another way is x square from here and another x square from here. So 2 plus 2 is 4. So that way we can get all possible summands. We are not allowing 0, that is why x raised to 0 is not here at all, because in that compositions we are not allowing zeros, right. And the order is important here, because either 3 comes from here or 1 comes here, or 1 comes from here and 3 comes from here. It is separately counted, because the coefficient of x raised to 4 accounts for both such ways for forming x raised to n. Both of them adds one each more to the coefficient of x raised to 4, right. Now what is this? This is, yeah, this is just 1 minus 1 by x, sorry, x by 1 minus x, because this is what this we know, because you can take x out from here, x into 1 plus x square plus, that is it, that is x by 1 minus x, and this is also the same, that is square, right. So the I summand thing is just this x plus x square plus first term, second term is x plus x square plus, similarly I such terms are to be put, x plus x square plus so on, right. So what does it give? This will be giving x by 1 minus x whole power I, and look for the coefficient of x raised to n in the expansion of this. It is clear enough, because any thing of this form a2 plus say ai is equal to n. So corresponding to this we can create an x raised to ai from this, an x raised to a1 from this, a2 from this, and finally x raised to ai from this thing. So we will get an x raised to n corresponding to that, right, that adds 1 to the coefficient of x raised to n. On the other hand, any way in which you can form an x raised to n by taking some x raised to a1 from this thing, some x raised to a2 from this thing, that a1 a2 ai will add up to n, and that is one of the I summand composition of n, right. Therefore we are actually counting what we are looking for, right. Now of course we want the total number of so we could have gone and figured out the coefficient of x by 1 minus x raised to n in x by 1 minus x whole power I, right, but that is not what we want. We want the total number, right, namely we want to find the coefficient of x raised to n in this x by 1 minus x whole power I, and this I is, because 0 is not necessary, because we are starting with one summand only, right, there is no 0 summand composition of n. So I equal to 1 to n, not more than n, because there is no n plus 1 summand composition of n. It is not possible, one of them has to be 0, right. We are only allowing positive integers here, 0 is not being allowed. So this only is required, but because you are looking for the coefficient of x raised to n in the product of all these terms, we can as well put this till infinity, because why? Because that is not going to change. The reason is because we are taking the terms of the form x plus x square plus x cube. So, the first term has to contribute at least 1 x, it is not that there is an x raised to 0 possible. So, x raised to 1. So, the second has to contribute at least an x, 1 x. So, by the time you cover n terms, the product already accumulated x raised to n. So, therefore, these terms, that means x by 1 minus x to the power n plus 1 kind of terms will not have x raised to n with non-zero coefficients. Why? Because this there are x by 1 minus x appearing n plus 1 times here. Each of these x by 1 minus x is of the form x plus x square plus this thing, and each are contributing at least 1 x. So, if there are n plus 1 such things, the power of the smallest power of x in the product has to be n plus 1. It is not possible to have x raised to n there. So, the coefficient of x raised to n in the expansion of this thing is going to be 0. So, that is not going to trouble us. So, here because this is a sum, the first n terms only will contribute, we can add the remaining things x by 1 minus x to the power n plus 1 onwards freely, that is not going to disturb us. Why am I doing the summation till infinity? To make things easier, that is all, right, because the calculations are easier when you sum all the way to infinity rather than the partial sums, right. So, now what will happen to this? So, we need to do some manipulation. So, first what we do is, so we look at again the sum I equal to 1 to infinity x by 1 minus x whole power I. Put y equal to x by 1 minus x, some change of substitution, right. Then this will read I equal to 1 to infinity y raised to I. So, how will it look like? This will be y plus y square plus y cube plus and so on. You can pull out one y from it. So, this is y into 1 plus y square plus so on. Why did we do this? Because this is easier to sum, we know the formula for that. Therefore, we have a y into 1 by 1 minus y, because that was 1 by 1 minus y. This portion is 1 by 1 minus y. So, we have y into 1 by 1 minus y. So, now we can substitute this one y equal to x by 1 minus x in this thing. So, x by 1 minus x is substituted here, and here we have 1 by 1 minus x by 1 minus x. So, here we can do 1 minus x minus, so this will become same, and now this can cancel off with this, right. So, this will become x by 1 minus 2x, this is the answer. Now, our answer is namely the number of compositions of n will be equal to the coefficient of x raised to n in this, and we already know that the coefficient of x raised to n in this will correspond to the coefficient of x raised to n minus 1 in 1 by 1 minus 2x. So, we only have to look for the coefficient of x raised to n minus n in 1 minus 1, this one, and this is familiar, we know this corresponds to the sequence of 1, 2, 2 square, 2 cube and so on, and we are looking for the n minus 1th term here, n minus 1th term here. What is that? That is 2 to the power n minus 1. This is what we got earlier also, right. So, we managed to get the same answer using the method of generating functions. So, this was a nice example because here things were like we were getting familiar generating functions, closed forms till the end, right. So, somehow it was it kind of cancelled off and came to this nice final generating function. So, that way it was nice. And now let us look at so another example. So, what about compositions of this form? Hn denote number of non-negative integer solutions of the equation 3 times E1 plus 4 times E2 plus 2 times E3 plus 5 times E4 is equal to n. Find the generating function for this sequence. So, what we do is, here we do a kind of conversion. So, 2 times E1 plus 3 times E2 plus 4 times E4, sorry E3 plus 5 times E4 is equal to n. What we do is, we make some substitutions first. Let us say F1 is equal to 2 E1, F2 is equal to 3 E2 and F3 equal to 4 E3 and F4 is equal to 5 E4. So, not for E1, E2, E3, E4 we have just the condition that they are non-negative integers. But now we are looking for the solution of F4 equal to n, F1 plus F2 plus F4 equal to n, where F1, F2, F4 has some extra conditions, namely F1 has to be a multiple of 2, that has to be an even number, sorry F2 has to be a multiple of 3 and F4 has to be a multiple of, so F3 has to be a multiple of 4 and F4 has to be a multiple of 5. How many such solutions are there? You can easily verify that that count will give the count for this thing, because if you get a solution for E1, E2, E3, E4 here, that corresponds to a solution of F1 plus F2 plus F3 plus F4 equal to n with the specified condition, namely because F1 is going to be 2 times E1, that is going to be an even number, F2 is going to be 3 times E2, it is going to be a multiple of 3, F3 being 4 times E3 is going to be a multiple of 4 and F4 being 5 times E4 is going to be a multiple of 5. On the other hand, if you get a solution here, you can find solutions for E1, E2, E3 and E4 by dividing by the corresponding factor. For instance, F3 value we have to divide by 4, we will get an E3. Why? Because F3 is indeed here the solution restricts F3 to be a multiple of 4, you can divide by 4 and we will get an integer, right, positive integer, sorry non-negative integer. So, therefore, that will be E1, E2, E3, E4 which is obtained that way will be a solution for the first equation. So, we just have to work with this stuff. Now, what is the generating function for this thing? This is easy, because F1 we will have a term like this. So, for F1 we will have a term like 1 plus x square plus x raised to 4 plus x raised to 6 plus and so on. That means only the even powers of x are taken here. For F2 it has to be a multiple of 3, right. So, we will have 1 plus x3 plus x raised to 6 plus x raised to 9 plus only multiples of 3 will come as powers of x. And the third form for F3 we will have 1 plus x raised to 4 plus x raised to 8 plus x raised to 12 and so on. And finally, we have 1 plus x raised to 5 plus x raised to 10 plus x raised to 15 etc. for F4, because it has to be a multiple of 5, right. That is the way we have set up these things. The power of x here is always multiples of 5, the power of x here is always multiple of 4 and power of x here is always multiple of 3. Now, we can simplify this thing. This is going to be 1 by 1 minus x square, this one is 1 by 1 minus x raised to x cube, and this is 1 by 1 minus x raised to 4, and this is 1 by 1 minus x raised to 5. Multiply this out, and we have to find the coefficient of x raised to n in the expansion of this thing if you want to get the answer, right. So that yeah, so you can get it as a sum of some complicated sum probably, but we won't try it out here. Now the next theme we have, so for instance there is a very interesting use for these generating functions in the context of recurrence relations. So in the last before a few classes we were discussing recurrence relations in detail, and we have given several methods to deal with linear recurrence relations with constant coefficients, homogeneous or non-homogeneous. We were giving several methods. So and here we will see how generating functions can be used to solve recurrence relations. In the case of linear homogeneous recurrence relations with constant coefficients of say order k, we will show that this method will always work. So this is like a recipe which you can simply use. You don't have to you don't have to think much here, it's just use it. Of course there is some difficulty later, because when once you get the generating function we have to find a way to extract the coefficients. That is the real difficult part, but there also we will see some methods are helping. So that is what we are going to discuss now. We will take some example and do. The first example is this one, hn equal to 5 hn minus 1 minus 6 hn minus 2 n greater than equal to 2. Of course this will work only for n greater than equal to 2, because you are depending on two previous terms, right. So 0 1 then 2, right. Initial value 0 for h0 and h1 has to be given. H0 is equal to 1 and h1 equal to minus 2 is given here, right. Now how will we solve it? So 5 hn minus 1 minus 6 hn minus 2. This is only true for n greater than equal to 2, and your h0 is equal to minus 1, h2 is equal to h0 is equal to 1, h1 equal to minus 2, h0 is equal to 1 and this is minus 2, right. So what we do is we write this in this form, hn equal to hn minus 5 hn minus 1 plus 6 hn minus 2 equal to 0. This is the first step. This is our step 1. In the second step we write like this, the generating function, say g of x, or we can write say h of x, say h0, yeah, maybe you can put h of x equal to h0 plus h1 times x plus h2 times x square plus and so on. Now what we do is we take this minus 5 and multiply this h of x here. So minus 5 into h of x we find. So what do we get? Minus 5 times h0 minus 5 times h1 times x minus 5 times h2 times x square. So what we do is that we will align this x terms So now sorry, minus 5 times, sorry, what I do is minus 5 into x minus 5x I used to multiply this h of x, right. So what happens is minus 5x times h0 will come, minus 5x times h1x will come, that is x square, right, and so on. So to align x terms and that power of, for instance, x raised to I term should come just below this, that way we will write. So therefore we will put a gap here and we will start here. So that means this is minus 5 into h0 into x plus here minus 5 into h1 into x square and so on, minus 5 into h2 into x cube and so on. Now in the next step what we do, we go back and see here it is plus 6. So we take that plus 6 and we will use 6x square to multiply hx. So now what we get, h0 into 6x square plus h1 into 6x square into x, that means 6x cube and so on. To align the power of x raised to I in the same column, right, same. So for instance below here I need the power of x square. So here the first term itself will contain x square, therefore I will put a gap here all the way up to here, and here I start saying 6 into h0 into x square plus next term will be 6 into h1 into x cube and so on, like that it will keep on going. So now what we do is we sum this up, we add all the, so this is say equation 1, this is 2 and this is 3, we add 1 plus 2 plus 3. So here we have h of x into, so this is 1 plus, sorry that not plus, minus 5x plus 6x of x square into hx. This is what I get here. Here what do I get? I get h0 first because there is nothing below here, right. Here I get an h1 minus 5h0 into x. Next term will be an h2 minus 5h1 plus 6h0 into x square, and plus the next term will be h3 minus 5 h2 plus 6 h1 this term, right. So here we have h2, h3 here, h3 x cube, okay. Here we have minus 5 h2 x cube, right, and here we have 6 h1 x cube, right. So h3 minus 5 h2 plus 6 h1 x cube, and from now on it will be the same thing, h4 minus 5 h3 plus 6 h2 into x4 and so on. So what is good about this is that this one h2 minus 5 h1 plus 6 h0, this is familiar. Why? Because hn minus 5 hn minus 1 plus 6 hn minus 2 is equal to 0. You put n equal to 2 here, so this will become 1, this will become 0. So that will become h2 minus 5 h1 plus 6 h0. That is exactly what is written here. So this coefficient is getting 0 by the recurrence relation given. Similarly this coefficient will also become 0 if you put n equal to 3. So h3 minus 5 h n minus 1, that is h2 plus 6 h n minus 2, that means h1. This is also going to be 0, and the next term is also going to be 0 because that is h4 minus 5 h3 plus 6 h2. So, all of them will become 0 and they all will vanish, this will vanish, this will vanish, it will go away. So, we only have this h0 plus h1 minus 5 h0 times x in this side. This side we have this, that is interesting. But this h0, h1, h0, this h1 and h0 we already know. What is this? Here h0 is h0 equal to 1, h2 is equal to minus 2. We can substitute that here. Say here I use 1 and this is minus 2, this is 1. That is 1 minus 7x, 1 minus 7x. This is equal to 1 minus 5x plus 6x square, 1 minus 5x plus 6x square into h of x. This is what we got. Yeah, 1 minus 5x 6x square into h of x equal to 1 minus 7x. This is what we got. So, h of x is what? H of x equal to 1 minus 7x by 1 minus 5x plus 6x square. So, we got the generating function for h of x. So, the sequence, see the sequence was h0, h1, h2 etc. right, and h0 value was 1, h1 was given to be 2, and for the remaining things we just had that recurrence relation, namely hn equal to 5, hn minus 1 minus 6, hn minus 2. This is what we know. From this thing we could derive the generating function for the closed form for the generating function h of x, right. The generating function h0 x, h0 plus h1x plus h2x square plus h3x cube, its closed form we got, that is 1 minus 7x by 1 minus 5x plus 6 square. Note that this is already captured the initial conditions also, we do not have to struggle to fit the initial conditions, right. It has also captured the recurrence relation. Now, we just have to get the coefficient of x raised to n from this thing, that will be hn, because this generating function h of x which we have written as 1 minus 7x by 1 minus 5x plus 6x square is can also be written as h0 plus h1x plus h2x square plus, that is hn x raised to n and so on. So, the coefficient of x raised to n is indeed hn. So, if you can expand this and get the coefficient of x raised to n in some different way as a closed form, then we got an expression for hn. So, how will you do that? So, here we have to use the method of partial fractions. So, not necessarily, but that is a very helpful tool. So, 1 minus 7x. So, first you factorize this thing, 1 minus 5x plus 6x square is in fact 1 minus 2x into 1 minus 3x, is not it? Yes. Now, I will do it in the next class, I will complete this in the next class.